And that was an oral final exam. Put us all in rooms and gave us a problem and then came back around. One girl in the room next to me had a nervous breakdown. Just started crying and so I was like, I don't blame her though. It's kind of just a bit intense. So I like to give as many grades as I can because that's a little fresh in my brain. Any questions on stuff we did last time? Anything from chapter 8? Put this up here real quick. One compositional problem. One hypothesis. Yeah. 34?
Yeah.
So this one is asking, use the given information to find the p-value. Also use a point of five significance, blah, 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 blah. So, very quickly, a little background. We normally do like a z-test. Like we have a value here, 1.645. So if we get 1.81 or something for our z-star, could you tell me right now if we would reject or fail to reject a null? Which would happen? Which would we do? This is the critical score. This is my benchmark. And what if I find a 1.81 for my z-star?
Reject.
We would definitely reject it. Now can you tell me, just from the picture, the p-value for 1.81? And versus, what's this whole area right here? What's this whole thing? Who remembers what that would be? What's in the tail? What? That's the rejection region. What's the area in that tail? They actually have to tell me so I can find this, don't they? So that area in the tail, how do we set up the rejection region? What do I have to look at? I have to know if it's a 1 or 2 tail test, but then what do they give me that actually lets me look it up? Alpha. Alpha is the amount in the tail. So in the book kind of shows you the two main ways to do this. One way is called the traditional method. And that's really just alpha tells me a benchmark z-score, and then I check my sample to see where it falls. Did it make it far enough away or not far enough away? Very straightforward, very easy. Right? Basically, if my z is bigger than that, more negative or more positive, we can reject the null. That's the idea. Cool? But look at this. Here's the alpha. If I reject that, we would if it was 1.81 z-score. Can you tell me from the picture, is the p-value bigger or smaller than alpha? So right now, you guys, some of you guys are like, how the hell would I know? But think about it. What is the p-value? That's the area in the tail of what? How do you find the p-value? What do you look up?
X over N.
That's p hat. I know it kind of sucks. There's p's and then there's p-value, but p-value is the area in the tail of your z-score. So this would be our z-score. This one is the critical z-score. So the area in our tail, how would it relate to the area in the 1.645 tail? How would our tail match up? Would there be more or less? In this tail, is there more or less than in this tail? Less, right? So in this case, the p-value would be less than alpha. So think about it. If to reject a null, I have to get further away than something, the area in my tail is automatically going to have to be less than the area in this guy's tail because I'm further away. There's less stuff out there. So another way to answer this whole problem, instead of looking at 2 z-scores, I can look at 2 areas. If my p-value is less than the area from the level of significance, I can reject the null. If not, I can't. So let me say this one more time. The traditional method is very simple, and that's the way I start, because it makes the most sense. Tell me how far I've got to get away, and then I'll see if I made it that far away. That's the critical z-score tells me how far I've got to get away, and then my z-star for my sample tells me how far I actually got away. A whole other way to look at it, instead of comparing two z-scores, I can compare two areas. If the area of my z-score is smaller than the area of the critical z-score, I must have gotten far enough away. I must be further. My tail is smaller. So this is equivalent to z-star greater than some z-score, right? In this case, greater than 1.645. Okay. This makes more intuitive sense. This less than freaks people out. They're like, no, I've got to be far enough away. But the further you are away, the smaller your tail is. And what shows me more evidence? A big p-value or a small p-value? I kind of gave it away with the emphasis. Yes, it's small. We've known since the first week there were problems in the homework that said p of 0.0001. We knew that was significant because it's so freaking small. And this tells you, but the smaller it is, the more significant it is, the further it must be away. All right, so I forgot who asked me the question now. Yeah, so you're sitting there saying, that's great, Jeff. What's this got to do with me? Well, here's what it's got to do. Which one was it again? It's been too long. 34. So with an H1 of alternate hypothesis of P not equal to 3/4, and the test statistic Z equal to 0.35. Now tell me, just looking at this, and this test statistic is another name for the Z star. It's my sample Z score, cool? My sample Z score that tells me how far my sample got away. So this is really just another name for Z star. Yes, ma'am.
I have a quick question. What section is this one?
Oh, I'm sorry. Section 8.2. All right. So looking, I don't even know what alpha is right now, right? I have no idea. Do they tell me? They tell me 0.05. But what I've written, I have no idea, right? I forgot to write it down. Even without writing alpha down, do you think this is going to be good enough? So let me put this is Z star then, right? The book doesn't call it Z star, it's just me, but let me put that there so we can relate it more to what I said. Is that good? Getting a Z star of 0.35, if my whole purpose of a test is trying to reject the null, do you think that would reject the null? Is that very far away from the middle? What's the middle? What's the middle Z score, right? The mean would be what Z score? 0. Is that very far away from that? No, it's just a little more than a third of a freaking step. It's not even a half a step away. So that is not very far away. So this is exactly the same thing. If you flipped a coin 50 times and you got 30 heads, you didn't get exactly half, did you? You got 30 heads. Would you be freaked out if you got 30 heads flipping a coin 50 times? Would you go, oh my God, holy crap? Would you? No, because it's not very far away from what you expected, right? You would expect 25, but we know it doesn't have to be exactly 20. Hell, it could be 50. That would freak me out. But it's still possible, but what's more likely in that case would be something's freaky about the coin, right? Or I'm about to get struck by lightning. I don't know, something weird's going to happen. But that is not very far away at all. Most of our critical z-scores we've seen have been like 1.645, 1.96, 2.33, that kind of thing. They got to be decently far away to show something. That's not very far away at all. So I'll bet you my p-value is going to be pretty damn big. It's going to suck, right? It's not a very significant finding. So if I draw this picture, what would this look like? Where would that be on this picture? Can somebody...
Close to the middle.
Say again, sorry?
Close to the middle.
So right in the middle is 0, so it's going to be about right there. There's 0.35. Where is the p-value? And again, what is a p-value? Physically, it's an area. You with me? Alpha is the area in the tail of the critical z-score, my benchmark. The p-value is there in the tail of my z-score. That's why I can compare them. So the p-value is this. And actually, tell you honestly, I got to be careful. So we get this area here. There's one little thing I think you guys remember from last time. How many tail tests would this be? 2 tail. So I have to look up this area, and then I have to double it to make it fair. Right? This is a 2-tail test. So can somebody help me out? If you look up 0.35, can you get the area that's up here? So if you look up 0.35, what do you see? What area do you see for 0.35? Don't sit back and wait for somebody else to do it. They might get it wrong. Screw them. Look it up. So what's the area of the tail of 0.35? So we see 0.6368, and that's here, of course. So the tail would be 1 minus that, 0.3632. So the p-value in this case, to make it fair, since it's a 2-tail test, to make it fair, I double that thing. So the p-value would be 0.7264. That's freaking huge. What that really means is there's about a 73% chance that what you found would just happen randomly, right? That this really probably is the real middle. That what you found really wasn't far enough away. There's a 73% chance that you would find that even if that was the middle, so it's not proof that it isn't. Didn't get far enough away. Okay. All right, maybe. So you can compare 2 z-scores, and that I hope right there by itself makes sense. We've done that before. What's unusual, what isn't unusual. The only thing that's really changed about that earlier idea is it doesn't always have to be 2 now, right? It could be 2.33, could be 1.645. That tells me what shows something weird is going on, right? Just like the penny thing. If I flip 50 times and get 50 heads, that is something weird. Why? Because it's far away from what I expect to get, 25 heads. But 27 heads, 30 heads, who cares? That's pretty close to what I expect. And tell me, personally, what would be a weird number of heads if you flipped the coin 50 times? What would freak you out?
25.
All right.
You get something like 45 hits on 5.
Yeah, like 45 might freak you out.
51.
Well, that would definitely freak me out. You're right. Let's stick within the 0 to 50. Would 40 freak somebody else out? I mean, if I got 40 heads out of 50, that would freak me out. But do you see how it's not the same for everybody? Right? It's not the same for everybody. That's why the critical z-score can change. It can move. It's not the same for everybody. You're trying to prove to an insurance company you should lower my rates. They're going to set their own freaking z-score, and it's probably going to be kind of far away. You got to show us really good evidence before we lower your rates because we like your money. Okay. So, finally, to answer this question, the p-value is way too big. My alpha was 0.05. Is the p-value less than alpha? Obviously not. So here we would fail to reject the null, fail to support the high. It's not less than. I mean, I didn't get far enough away. We knew that from the beginning. We didn't get far enough away. This is just further verification. Okay. Maybe.
Could you go over 42 with that type 1 and type 2 error?
Yeah. All right, let me do this up here. I'd like to talk about errors in terms of something in English for a second, and then we can apply it to something in mathish for the stats stuff. And you know, in keeping with the theme of the book, it seems every now and again it's got something very morbid in there. Deaths and cancers from cell phones and stuff. if I were to go out into a battlefield, I'm a medic in the Army, and I'm going to go out in the battlefield, and I'm going to try to help the people that I can help. As I approach somebody, what do you think I'm thinking about them? Am I thinking they're dead, or am I thinking they're alive?
Alive.
I'm probably thinking they're alive, and I'm checking in the test to see if they're actually dead or not, right? So in this case, the null could be they're alive, and the alternate would be that they're dead. Now, there are two big mistakes I can make. So if I approach somebody and they're really alive, but I feel for their pulse, and either I'm like overly excited because there's bombs going off everywhere, or their pulse is so low I don't feel it and I think they're dead, is that bad? Because I'm not going to help them, right? I'm going to move on to somebody. Well, they're dead. I can't help them now. Let me move on to somebody else. You kind of with me so far? So that is one type of error to make. In that case, in reality, this was true, but I rejected it. You with me? Because in the background of all these tests we're doing, the tests, there's always a chance that I'm wrong. Therefore, there's always a chance that I make a mistake. And statistics does not claim to be perfect. It says, shit, man, you can make mistakes. And that's why we're allowed to change this. How bad is a mistake? Let me change that so I don't make that kind of mistake. So one way to make a mistake, and that's the type 1 error. Currently I have to call type 1 and type 2 because there are two of them. The never-ending creativity of statisticians. Type 1 error is that I reject a true null. So to put it in more English terms, I thought they were dead when really they were alive. You with me? So this is kind of nice. I like this. You can see the person out in the battlefield. The test they're applying is something physical. They're feeling for a pulse, seeing if they're breathing. You with me? So they're applying like a real test that you can actually see and feel. And they reject this and they support this, so they move on. What's the other type of mistake I can make?
If they're dead and you think they're alive.
Exactly. I make a mistake and feel for the pulse with my thumb, which is stupid because then I feel my own pulse, right? You guys know that? So I feel my own pulse, or I think they're breathing when really it was just something else. I don't know. And that could certainly happen. I would not fault any medical person for making that mistake in the middle of a freaking war, right? But these are the kinds of mistakes that can be made. So the other error would be, I think they're alive when they're actually dead. So if I think they're alive, did I reject the null? No, I failed to reject the null. I tested, and I failed to reject. I didn't see anything that they were dead, right? So I fail to reject a false null. Now, on one level, even though I haven't said that before today, that's always been possibilities. If I reject a null, it might actually be true. If I fail to reject it, it might actually be false. Statistics can't possibly say anything about what actually is true because we're only taking a sample. He only did the pulse and the breath. He didn't do it. He didn't have time to do anything else. So it's a very limited sample that he's trying to work from. He could very easily make one of these mistakes. How's that so far? Is that good? And that's plenty, I think. I'm not going to focus too much on those. I just want you to be aware that, like always, statistics is one of the most honest branches of mathematics. It even says, here, let me tell you the mistakes I can make. There they are. Type 1, type 2. If you had to memorize these, and I'm not going to make you, type 1 is the shorter phrase, reject a true. Type 2 is a longer phrase, fail to reject a false. That's how I remember it in my head. Okay, is that cool? So then you do exactly that for the problems in the book. Like 42 says, the percentage of Americans who believe that life exists only on Earth is equal to 20%. So would that be the null or the alternate? Yeah, it's got an equal sign in it. What would the alternate be? What's a type 1 error that you could make? You could find evidence that this is what's a type 1 error that you can make? Type 1 would mean you reject this when really it's true. So you find evidence that this is false, you reject this, when really, in reality, it's true. Your sample may be, and again, I want you to understand, anytime you take a truly random sample, you could just happen to pick older people or people that don't have cell phones or whatever. In this case, I could just happen to pick a bunch of people that think that there's life. In fact, as I'm talking to them, they have their foil hat on and everything. Right? Should be a sign to me. Maybe I should vary my sample up a little bit. But I get like 87%, so that's obviously going to blow this away. But I just happened to pick a bad sample. So truly random samples, are they always good? No, but they're the best we can do. I can just happen by chance to pick a lot of people that sway one way or the other. And that's why these tests have built-in mistakes that you can make. I can't help but make mistakes sometimes. All right, so how are we doing so far? Is that cool? If that's all you got to say, then type 1 error would be, I think it's not 20% when it really is. A type 2 error would be, what? We think what?
Don't reject.
Type 2 would say we think,
It's not 20%.
that was type 1. Type 1 is reject a true null. So I think it's not this when it really is. Type 2 is fail to reject a false. I think it is 20% when it really isn't. That kind of question then becomes very simple. Right? It's just two possibilities. Okay, maybe. Any other questions from chapter 8? If you came in just a little while ago, I just want to point out we have a quiz on Tuesday. 1 confidence interval problem and 1 hypothesis test problem. Okay. So, I actually have no plans to talk any more about hypothesis tests today. So I'm just going to go purely off of any questions I got. I want to get into chapter 10 today. Chapter 9 I'm going to talk about very quickly, and I'm actually going to make it extra credit. Yes. I just want to very quickly show you how the formulas change. Chapter 9 is all about, you don't just take 1 sample, you take 2. Because remember in chapter 8, the very first type of thing we did was somehow we magically knew the standard deviation. And actually that was back in chapter 7 with confidence intervals, when in reality we normally don't. You with me? So that's why we had to invent what? What saves me when I don't know the population standard deviation? I have to use what? T-scores. If I only have a sample to get stuff from. You with me? So normally I don't have a population idea of the whole population at all. So if I wanted to see like the difference between men and women over the last 10 years in my stats classes, I don't really have like a population to work with because it could have been, people dropped out. Who knows how they could have done. I've just got the sample of people who actually ended up taking my final exam and getting grades. You kind of with me? So I've only got two samples then. I got the sample of women and the sample of men. So I need a formula. The formula from chapter 8 basically looks like this. Let me put it all in here at once. Is that cool? It's not the way I normally write it, but that's just everything in its full glory. There's the new standard deviation. There's the R data minus the middle. The only difference if it was a T would be, that would be S, right? So it's really the same formula. Is that cool? Sort of? Okay. So if I take 2 samples, I'm going to have an X bar 1. I'm going to have an X bar 2. I'm going to have an S1 and an S2. And I'm going to have an N1 and an N2. So if I took 80 women and 107 men as a sample from all my stat students in the past however many years, this might be the women, 87 women, I can't remember what I said now. And I can find the average grade, I can see the standard deviation in the grades, and I can do the same thing for the men. What would mu1 and mu2 then be? These are my women, these are my men. This would be that thing that I don't know, right? I don't know the population, but I'm trying to get a feel for this, how different these might be based on these samples, okay? So again, this is kind of nifty. All the steps are the same, all 5 steps, exactly the freaking same, exactly the same. The only difference, the only real difference is this becomes this, and this is where people kind of freak out. But I desperately want you to see how it just doubles everything. Why? Because there's 2 of everything, right? So on top, I wouldn't just have x bar minus mu. I'd have x bar 1 minus x bar 2 minus mu 1 minus mu 2. I double everything.
It's going to be minus mu1 plus mu2 without parentheses.
Sure, if you want to. What we normally assume, what we're normally working against, what do you think? If I'm looking at, is there a difference between women and men? Let me just say that the way it is, and let me see if you guys can answer this. If I'm saying I think there's a difference between women and men, the grades in my class, would that be HO or H1? I think there's a difference between women and men. I think women and men's average grades are different. So that would be mu1 not equal to mu2. 11, so that'd be H1. What would HO be? That they're equal to each other. If they're equal to each other, what's this? 0. So normally that's not even there. You with me? Normally we're trying to show that there's a difference. Therefore, the null must be that they're equal. So this would actually go away. Again, right now you're all sitting there thinking, okay, do I understand this well enough to even try this extra credit? I can hear it. But I desperately, that's what we pretty much, when you do a drug trial, and you do a sample of the old drug and a sample of the new drug, that's more true to life, isn't it? I do a sample of the old, sample of the new, with control groups. What am I fighting against? That they're the same. I want to show that they're, actually I probably want to show that one is quicker than the other one or something, but I'm always fighting against the fact that they're the same. So this almost always just goes away. So that's why I wasn't really too worried about distributing the negative.
Yeah.
Now, let me see if I can get you guys with me on the bottom. Very quick algebraic side note. Is it okay for me to do this? Are you guys cool with that? By the way, I want to show you. Okay, cool. Where's it there? Okay. So that's cool, right? And this works when I have one sample. But what if I have 2? I just need 2 of these things. So I'm just going to need this one there and this one there. So that this formula is the same as this one. It's just that everywhere you see sample stuff, there's got to be 2 of them. That's it. That's all chapter 9. That's the only real difference in chapter 9 is that formula there. Critical region, p-values, all that kind of crap is the same. Setting up the hypotheses, telling me can you use z-scores and t-scores, it's all the same. Conclusion, same. The only difference is this.
Yeah, so the formula pretty much gets boiled down to x1 minus x2 over square root.
I love it. And that to me makes even more conceptual sense. So normally this is not even here, right? So in order to show evidence that women's grades are different from men's grades, what would you have to say about the 2 sample averages I find? Don't they have to be far away from each other? The difference between them has to be big. So the bigger the difference is here, the bigger the z-score is going to be, the more evidence I see. And that goes right along with what makes freaking sense. If I think women have scored higher than men, then the women's average better be freaking a lot bigger than the men's average from the samples I take, so my z-score ends up being big. So that actually, taking that away, it ends up making more conceptual sense with that out of the way. Is it always 0? No, but we're not going to get into that. I don't think I solved any of those problems. Okay. And the same thing with, well, I'll do this. I'm not going to get into it. The z-score for p hat and p problems, it's a little bit, well, it's basically the same, except I don't know how deep I want to get into this. So there's what I expect on the top. Right, the two differences, and this is on page, nope. Oh yeah, 9.2, so it's on page 451. So instead of having 1 PQ over N, I now need 2. I'm going to have P1 Q1 over N1. And actually what I end up getting is not that. I end up getting what's, I'm going to let you guys, if you want to do this extra credit, let me see if I can actually get it written up here. Let's see if we got that right. It's been a while since I did this one. Yeah, cool.
That's simple.
So this P bar,
Oh, Q bar.
yeah. So I'll let you guys look that up if you want to. What it really is if I had 10 women out of 30 who did something, and I had 12 men out of 47 who did something, P bar would be the whole thing at once. This many people out of this many people. P bar is what they call it's like a pool. You pool everybody together. You don't segregate people. You put them together. So men and women, P bar would be just freaking people. Right? The total people that did something divided by the total number of people. Okay. So these formulas, when you look at them, they look a little disgusting, but they're actually not that terrible. And the whole format of the hypothesis test does not change. So I'm hoping a few people attempt chapter 9. Okay. It's just that, I don't know if you realize this, but next Tuesday is the last day we have to talk about new stuff. Because then we're going to have the review on the Thursday for the last test. The next Tuesday is the last test. The next Thursday after that is review for the final. And then the next week after that is the final. So there's no time for new stuff after this coming Tuesday. So you don't like think, yep.
Are you going to give us a practice test for the final?
Practice final, yes. Cool. I have a practice final I will give you. I'll probably give it to you. I might even give it to you next Tuesday just so you have it for a long time. And then I give you the answer key on that last Thursday for review day, yeah.
Am I going to touch chi-squared?
Say again?
Am I going to touch the chi-squared stuff?
Chi-squared only, it's not going to be on there. I'm going to hopefully, one of these days, I'm going to talk about it very briefly. Anybody looking to become future, are you psychology majors out there? Anybody? Psychology? Psychology?
Minor psychology.
Okay, gotcha. So you would be one of the few that would really immediately be curious about chi-squared. But there's uses for it beyond psychology, but that's the one that uses it a lot. Okay. So this is all I'm going to say about chapter 9. Right there. So it's up to you to decide if you want to try it out.
So what will be on the test then?
If it's, I will tell you this, I will have one bonus question, so that if you do choose to do this, you can also get bonus credit on the exam. So, what I want to focus on today, and if you had a lot of trouble with chapter 8, this might be kind of nice, because this is entirely different. So you can let go of that. It's entirely different. And it's actually going back to something we talked about a long time ago. What was it about correlation? If I find a correlation between two things, what was it we had to be careful about?
It's not causation.
Yeah, it doesn't mean causation. So we had that really silly example of the guy who went and watched people playing basketball. And he said, oh wow, if you play basketball, you get taller. He thought that playing caused height growth. When really, normally, height growth causes playing. or at least continuing to play. So chapter 10 is all about correlation. So we're really going to get down into testing for correlation. When I say that, I want to be careful. It's not a hypothesis test. It's just identifying data to see if we can tell if there's a correlation or not. So let me do this. I've got a nice little handout. It's actually the lecture I gave when I videotaped my lecture to get a job here way back when. They told me later that a big reason I got the job was because I mentioned beer. So I'm like, well, I should tell my students, I just did. So one of these has something to do with beer. Get excited. I'm not going to bring beer.
Advice to mention beer when you get a job?
What's that?
Is there advice to mention beer?
No. Know your people. Know your audience.
Beer helps with statistics. This beer helps with statistics.
Yeah. Exactly.
All right. So if you just search on Google, and if I have time, I'm going to show you, if you just search Google correlation, and you might have to put it to like the last year or something, because a lot of the hits you get are just correlation explained. Correlation is not causation. Like, shit, I want an actual study that gives me something about correlation. You'll see them reference, maybe I'll do it right now. I'll show you one that I found really quick this morning that was interesting. We'll let that guy warm up. In the meantime,
That's me right there.
you guys see that right? That was very straight. There you
You really.
Found myself on the handout.
go. What's that?
Found myself on the handout.
Oh, yeah?
On that little dot right there.
In fact, let's talk about that real quick. We won't talk about Walid's drinking habits, but if you look at this, can you tell me, is there an overall trend? And let me just do this. Let me cover that guy for a second. Is there a trend? So as the number of beers consumed goes up, what do the grades tend to do? Go down. Now there's two main outliers here. Who's this person? Did they drink a lot? No, but they still didn't do well on the test. So obviously they didn't know much. So it doesn't matter how bad you drank the night before, your 7 a.m. test, you're still going to suck. This guy, who's this person?
That's me.
All right, that's Walid. He's drink a hell of a lot, and you might have a good tolerance for alcohol, and you still made a damn good grade on the test. You with me? So those are kind of like some outliers, but the general trend might be a downward trend. Okay, how are we doing so far? Now, what about this trend? What would you say? It's the same data, maybe for a different class or something, but what's the difference between this data and that data? Which one is stronger evidence for correlation?
This one's stronger.
Yeah, I'd say that those points are tighter to a line, right? And when I say a line, like I could draw a line like this. That's a graphical, like a visual average of all the points. This one would be a lot easier to draw, and they're all tighter to it. With me? So I eventually want to get a number that tells me how tight to the line my data points would be, which would be a measure of how good the correlation is. How are we doing so far? Yeah.
Not just the standard deviation.
No, for two reasons. How many variables do I have in my data? Two. Number of years and grades. So I don't really have a standard deviation for two variables to define. Plus, it's not really a standard deviation in the exact sense. It's a measure of how far away from the line I'm getting.
Instead of the point, how far away we are.
Exactly. Good. Yeah.
Isn't it something close to the slope?
The slope is involved, and in fact, if one is negative, so is the other one, but the numbers don't really match. R could be huge, but it could be very small slope. Okay. Look at the next group. So this is, of course, studying versus grades. So same idea there. Which one shows better evidence of correlation? First one. The second one is more realistic, really, right? Because you'll have this person. Who's this person? Studies his ass off, still doesn't make a good grade, right? Probably because he wasn't studying, right? And who's that person there?
That's also me.
That's you with the beers and the not studying. Yeah, people don't hate you. So this person barely studied at all, but they still made a really good grade because they kind of pick it up very quickly. Cool. Let me switch over real quick. I can't. That's too close. All right, so if you just type in here correlation, and if you tell it maybe the past year, this is what I did real quick right before class. A lot of this is crap, and I think on the third page, here. I haven't played with this. I had no idea Google had a correlation tool, so I'm like, my not well hidden inner geek just was like, oh, cool, I want to play around. But try to see what this is. What they did is they saw how often do people search in Google for filing for unemployment. How often do they search for that? And they plotted it. So that's in red. They plotted that versus the actual unemployment claims. So what they're trying to see is if you search Google and you see an uptick in the number of searches for this, you could predict that maybe the actual unemployment claims is also going to go up. Now, in a sense, this only makes freaking sense. You with me? And this is not what our data is going to look like when we graph it. We're actually going to plot the data points and see how closely related they are, just like the ones for the beer and the grades. But this is not a bad way to look at correlation either. They obviously correlate. When one goes down, so does the other one. When one goes up, so does the other one. Is it perfect correlation? Hell no, this went up and this went down a little bit, but overall, they follow each other. Cool. Okay, so I have to get in there and play around with that because I want to see what it's really like. So coming back to this, what's that?
People didn't know how to Google in 2003.
Good point. 2003, there wasn't much, not yet.
Yeah.
All right, so what we need to find, it would be great if we could find some way to find a number that would enable us to compare the strength of different relationships. One number that would tell me it's really strong versus it's really spread out, so it's really weak. And we call this thing the, where to go? Correlation coefficient or the Pearson product, and we use the symbol R. So R is always going to be between -1 and 1. So -1 would mean something like this. How much do the data points vary from the line? Not at all. So 1, either 1 or -1 means it's perfect correlation. In this case, it's perfect negative correlation. So this would mean the more that this increases, the more that this decreases, whatever they are, right? So this might be your level of income versus your health. I don't think it'd be perfect correlation, but it'd be decently strong. Not health, but like amount of time spent in the hospital. I don't know. Some kind of health related thing. So as one increases, the other one would decrease. That's -1. Perfect negative correlation. So what the hell is R equal 1?
It's going to be the opposite.
Exactly. R equal to 1 would just be perfect positive correlation. Cool. And it has nothing to do with the slope, by the way. I mean, if I made the slope a little less, R would still be 1 if they all lined up on the line. You with me? The slope is definitely positive if the R is positive, and it's negative if the R is negative, but I don't know how big the slope is. It doesn't tell me anything about that. It just says how close are the points to the line. So what do you think R equals 0 means?
They have a straight line.
Both of you
They're
are
all
right.
straight.
Either it's like exactly no correlation, and even this would actually have not 0. There would be some stupid little tiny correlation there. But it's really just spread out. Or this is really misleading. That is also R equal to 0. And what this would mean would be like the height of the building over there versus how high I jump. So I don't care how freaking high I jump, the building's not going to grow. You with me? That's a really stupid example, but there's absolutely 0 correlation between me jumping and the height of that building. So that's why this flat line means no correlation. Or, of course, the other way. That would be no correlation.
What if you jump really high? Try it.
You'd have to be pretty damn fat to maybe make it drop a little. So, yeah.
I just want
So
to make
be
it
careful.
jump again, that's all.
Okay. And the last thing here, I haven't really made a point of this, but I'm thinking you guys might realize this. We're talking about linear correlation, just straight lines. So if I had something like this, and we had something like that a while back, remember the energy usage versus the temperature? When it's really cold or really warm, it's way up there. This would be R equals 0 for linear, but if I use quadratic, which we're not going to, don't worry, it would be maybe R equals 1. It lines up perfectly with a parabola. So for those of you that are all interested in further mathematics, you could do all kinds of correlations. Linear correlation, logarithmic correlation, power correlation, all this other stuff. And actually your calculators do most of those. We're only going to do linear. Okay, cool. So this would still be R equals 0 for linear correlation. So I'll tell you one really, really nice piece of news here. And it's going to not seem like nice news at first. If you have your book, look on page 498. That is the formula to calculate R. Now, let me just let it sink in for a second. We're not going to be using that formula. We're going to just use the calculator. This is the one chapter that I think doing the formula does not really illustrate the concept well enough when you just do it on the calculator. Because then I'm going to ask you follow-up questions anyway. But can anybody see on the bottom, does that look at all familiar to anybody?
Isn't like the standard deviation?
Yeah, that's a piece of the standard deviation. So this is like the standard deviation of my x's, the standard deviation of my y's, and it only makes sense that the standard deviation should show up here somehow, because it is roughly some kind of a standard deviation, a measure of how far away from an average line that my points are, but it's a lot more complicated than that. So yeah, honestly, it's called a least squares line. You want to get the smallest distance, and distance has to be squared to make it positive, so it's called a least squares line. How important is that for us? Not very. So I want to try to do a couple examples with you on the calculator. And of course I didn't bring any with me, so hopefully enough of you have one. So you all have this data on the back. The very first thing I want us all to do, if you have a calculator, you want to try this along with me, is what do you think you're going to do with these? L1, L2, I love it. So there's two variable data. So plug it into L1, L2. I'll do the same thing up here. Okay. Oh crap, didn't mean to do that. Let me ask you a real quick question that hopefully is obvious. Do you want to sort this data?
No.
Hell no. Because this 70 goes with this 4.5. If you sort it, you're always going to get a beautiful straight line. Or pretty straight, right? Because you're forcing them to go up here and up there. Everything's correlated, Jeff? No. I don't think you sound like that, but that's just me. So here's where you go. The very first thing, let me show you. I can't remember if I did this a while back, but remember we did scatter plots? And that's the one I was talking about earlier where you had to plot the temperature versus the energy use. And it ended up being like this. I don't know if you guys remember that way back when. I think it's section 1.3 or something. Or 2, I can't remember. But if I want the calculator to do it for me, I've put all these freaking data points in here. It should be able to just graph it. It is a graphing calculator that costs a lot of money, so it should be able to do that. I don't just want to go to y equals. That'll graph a line. I want to graph statistics. So obviously right above y equals, do you see how it says stat plot? That sounds promising. So hit second y equals. Again, anytime we do something on the calculator, I desperately need you to tell me if anything freaks out on your calculator, you get some weird error message. But right now, I want all of these turned off to begin with. So if you just hit 4, enter, it's going to turn them all off. I want to make sure that we don't have, some people have like all of them turned on. Let's just turn them all off. Now go back to second y equals. How are we doing so far? Yes, ma'am. So number 4 is plots off. So if you hit number 4, enter, it'll turn them all off. Cool. So I want to make sure we're starting off on the same foot. Yes, ma'am.
How do you get to stat
Oh,
plot?
second y equals to get up to stat plot right there. Cool. So second y equals. If they're all off already, you're good. So let's go into number 1. Plot 1. Hit enter with number 1 highlighted. Or just hit number 1. Is everybody with me? You want to turn it on first. So go ahead and hit enter when it, or on top of the on. So now it's turned on. What kind of plot do we want? Some of you guys might realize a little makeup box on the screen. Oh, like that. I'll make it screen. But yeah, we want the scatter plot, right? Evil teacher. So make sure that the scatter plot is selected. Highlight it, hit enter. My X's are in L1, my Y's are in L2. Cool? Want the number of beers there and the number and the grades there. And then you get to pick, are you a square? Are you positive? Are you a speck of dust in the universe? You can pick whatever you want them to use to put on your data points on your screen. You with me? So I'm obviously going to use a square. You guys can use whatever you want to. Now if you just hit graph right now, just hit graph, it's going to be a little bit not satisfying, right? And that's because when you hit graph, it's just going to show you the -10 to 10, -10 to 10. I want to tell it to zoom in on my data. So you hit the zoom button right here. Zoom. And if you scroll down for a while, you'll eventually see the one that makes sense. Zoom stat. So if you just hit the number 9, you can get there easier. Zoom stat. And we should all have this. So let me just stop there for a minute and make sure everybody playing along. Do you get that?
Oh.
Let me do that again.
So put in L1 else.
So you put your data in. If you have, now obviously everybody should have, hopefully, the calculator you're going to use on the test. The nice thing is after we do the examples today, it's all going to be set and ready. You don't have to do anything else. If it's today, you want to make sure that your stat plot is on. So go to second y equals, make sure that number 1 is on. Scatterplot, L1, L2, pick your symbol that you want. So if you do all that now, it's set and ready for the test. You with me? And of course, if you borrow a calculator, it's not necessarily going to be set and ready. If I hit graph, normally if I hit graph, it's going to show up like this. Whenever you put new data in, you always hit zoom 9 for zoom statistics. Yeah.
So I pressed graph and it gave me errors.
Oh, good. What's it say? Dim mismatch? Hopefully not.
It says clear to go to.
Does it say syntax? Argument. Neato. Hit go to. Now what's it on?
Gives me the plot and then y1 and y2.
Oh, good. So clear that. So the type of errors you get here, there are 2 main types of errors you're going to get. If the lists are not the same length, then not every point has an X and a Y. You with me? Because when you put L1, L2, that's really XY. It's like an XY table. So if you have one list longer than the other, the calculator goes, holy crap. How the hell do I plot a point with nothing in there? So one error could be dim mismatch, dimension mismatch. Your lists are not the same length. Syntax errors or anything else, especially when it says go to kicks ass. Because let me make the same error you had. There. Now if I try to graph it, I get a syntax, you got a argument, whatever the hell. But if you just hit go to, it's going to put the cursor on top of the problem. Make sure all this stuff here is cleared out. The most common mistake is to have some weird stuff in the Y1, Y2, Y3. So up here on the top of the page I gave you guys, I actually have a little thing about the errors that could happen. So make sure these are all cleared out. Now if you hit zoom 9, hopefully you should get there. Yeah.
Mine has a line through it.
Oh, go to your y equals and clear it out. So everybody's y equals should be all clear. Okay. Otherwise, it's going to try to graph lines, and that gets confusing. Okay. So is everybody with me now? Everybody's got this picture? And I tried to make it look like, I think I managed to do it pretty well. I tried to make it look like that one there. Right on the back, the beers and grapes. Okay, cool. So, can somebody predict for me? Is the R going to be, is it going to be negative or positive, the R for this? Negative, because I know it doesn't, it looks like maybe it's 0, but there is a slight trend. So is it going to be close to -1 or closer to 0?
0.
Closer to 0, because are my points really tight to some kind of a line? Hell no, they're pretty damn spread out. So R should come out to be a very small negative number, like -0.1 or 0.2 or something. Can you guys see that? All right. So now we're going to actually calculate 2 things. And just to let you know, in the homework, 10.2 only deals with finding R. 10.3 deals with finding the actual equation of the line. So I'm going to do both right now. In your homework, you probably want to do both of them. Just like remember way back with 2.2 and 2.3 where do the histograms. Same thing here. You want to do both of them at the same time. So here we go. Go to stat. And now, of course, I want to do something with the data that I put in there. So where should I go to actually do something with the data? Calc. Which one of these looks like the right one to use for what I want to find? Yeah, number 4. I want to find a line. And that actually stands for what's called linear regression, which is really what a line of best fit, that thing that we're trying to find, is. So number 4.